Welcome to today's paper reading. Today's paper is titled, PlanGPT, Enhancing Urban Planning with Tailored Language Model and Efficient Retrieval. This paper was published on the AR14 preprint by Zhou and colleagues from Peking University and other institutions. In the field of urban planning, general-purpose large language models often face limitations in meeting the specific needs of planners. Tasks such as generating urban planning texts, retrieving related information, and evaluating planning documents pose unique challenges. To address these issues, the authors introduce PlanGPT, the first specialized large language model tailored for urban and spatial planning. Developed through collaborative efforts with institutions like the Chinese Academy of Urban Planning, PlanGPT leverages a customized local database retrieval framework, domain-specific fine-tuning of base models, and advanced tooling capabilities. Empirical tests have shown that PlanGPT achieves advanced performance, delivering responses of superior quality precisely tailored to the intricacies of urban planning. The impressive reasoning, memory, and comprehension abilities of large language models, LLMs, have led to substantial progress in various domains, including finance, medicine, and law. However, urban planning presents unique challenges such as the government document style, the need for interdisciplinary knowledge, and the requirement for timeliness and multimodality. To address these challenges, the authors introduce PlanGPT, a specialized LLM for urban planning. PlanGPT features a customized embedding model and vector database retrieval system for accurate information extraction. It also employs instruction fine-tuning to activate interdisciplinary knowledge and enhance government document style proficiency. Additionally, PlanAgent, an agent-based system, is utilized to manage resources like networks and visual aids, effectively tackling issues related to timeliness and multimodality in planning documents. Figure 1 illustrates the workflow of the review task in urban planning. This process involves meticulously evaluating each item in urban planning documents against a standard framework. Staff members are tasked with identifying and rectifying any errors or omissions within these documents. This detailed assessment ensures the accuracy and compliance of the planning texts, which is crucial for the effective execution of urban planning projects. The related work section discusses the versatility of large language models, LLMs, in both general-purpose and vertical-specific applications. Notable models include ChatGPT, GPT-4, and Llama, with specific Chinese language models like Baichuan and GLM addressing unique linguistic challenges. In the urban planning domain, specialized models such as TrafficGPT, Prithvi, and TransGPT have emerged, with EarthGPT integrating remote sensing for enhanced perception. PlanGPT is introduced to fill the gap in urban and spatial planning. To mitigate hallucination issues, various techniques like retrieval, fine-tuning, and agent tools are employed, with notable works including RAG, Self-RAG, and FLAIR. PlanAgent is proposed to address these issues specifically in the urban planning context. Figure 2 provides an overview of the PlanGPT architecture, which is designed to address the unique challenges of urban planning texts. The architecture includes two main components, Vector LLM and Local LLM. The Vector LLM component features a customized embedding model called PlanEMB, which is tailored for understanding urban planning-specific knowledge. Additionally, it introduces a novel hierarchical search approach named PlanHS to improve information retrieval accuracy. The Local LLM component focuses on activating and developing urban planning knowledge within the model. This comprehensive architecture aims to enhance the model's ability to handle the complexities and specific requirements of urban planning tasks. PlanGPT is structured around three main components: Vector LLM, Local LLM, and PlanAgent. Vector LLM introduces PlanEMB, a specialized embedding model for urban planning, which includes a two-stage training process and uses influency loss to prevent forgetting. PlanHS, a hierarchical search approach, is also introduced to improve search accuracy. Local LLM focuses on activating urban planning knowledge through self-annotation and developing specific capabilities by fine-tuning on over 4,000 historical plans. PlanAgent assists urban planners by autonomously generating task lists, performing web searches for real-time regulations, and invoking domain-specific tools for tasks such as reverse geocoding and knowledge graph construction. Figure 3 illustrates the urban planning annotation process, which involves several key steps. First, high-quality unlabeled textual data is initialized from urban planning repositories, web archives, and knowledge graphs. This data undergoes quality checks, deduplication, and sampling. Second, the unlabeled data is segmented into multiple segments using varying window sizes and an overlap between adjacent segments to balance information integrity and granularity. Third, a scoring model is trained to assess the potential urban planning knowledge value of each segment, selecting those with higher scores as candidate segments. This process ensures that the data used for further annotation is of high potential value. Table 1 provides a detailed overview of the dataset statistics for various downstream tasks in urban planning. The tasks include text generation, style transfer, and information extraction. Each task is broken down into training, development, and test sets, with the number of samples indicated by the hashtag symbol. For instance, the text generation task has 100 samples for training, 1,089 for development, and 100 for testing. Similarly, the style transfer task involves 489 training samples, 1,181 development samples, and 489 test samples. The information extraction task has 138 samples each for training, development, and testing. These statistics are crucial for understanding the distribution and size of the datasets used to train and evaluate models in urban planning applications. The experimental setup involved curating a specialized dataset for urban planning, which included nearly 50,000 high-quality instruction pairs. This dataset was used to fine-tune the base model, enhancing its capabilities in urban planning. The downstream tasks evaluated included text generation, text style transfer, and text information extraction. Several baseline models were selected for comparison, such as ChatGLM 3-6B, E6B, and Quen 7B. These models were assessed based on their performance in generating urban planning documentation, transforming text styles, and extracting key information from textual sources. Table 2 presents the evaluation results of common urban planning tasks using various models. Key findings include PlanGPT's significant outperformance over other models, achieving an average 79% Spearman correlation coefficient to human assessment. However, the model still faces difficulties in making subtle distinctions in quality, such as differentiating between best and good. These results highlight PlanGPT's effectiveness in evaluating text within urban planning tasks. Table 3 presents the urban planning knowledge assessment results for various models. The models assessed include GPT-4, CHACT, ChatGLM 3-6B, BlueLM 7B, E6B, Baichuan 13B, and PlanGPT-8. The assessment scores are categorized into V1, V2, Average, and Delta. The Delta values, which are higher for more honest assessments, show that PlanGPT-8 has a delta of 0.812, indicating a strong capability in honest assessment. This table helps in understanding the performance of different models in the urban planning domain. Table 4 presents a comparison of embedding performance across various models, highlighting the effectiveness of PlanGPT in specialized urban planning contexts. The table shows that PlanGPT achieves higher scores in specialized datasets like URSDSB, demonstrating its superior ability to capture domain-specific information. Notably, BERT-CSE, after fine-tuning, significantly outperforms the base BERT model, emphasizing the importance of the initial pre-training stage. This comparison underscores PlanGPT's superior aggregational efficacy, making it a more effective tool for tasks involving urban planning terminology and language systems. Table 5 presents the results of ablation studies conducted on vector LLM to assess the impact of removing specific components. The removal of PlanGPT led to a 0.7% decrease in score, while the removal of PlanHS resulted in a more significant 3.6% reduction. Additionally, PlanHS demonstrated effectiveness in handling texts with low signal-to-noise ratios, enhancing overall information utilization and accuracy. Figure 4 illustrates the TSNE projection between PlanGPT and BERT-CSE. This visualization technique is used to reduce the dimensionality of the embeddings from both models, allowing for a clearer comparison of their spatial distributions. PlanGPT represents a specialized embedding for planning-related data, while BERT-CSE refers to a BERT-based model fine-tuned for sentence embeddings. The Tianle projection helps in understanding the similarities and differences in how these models represent planning-related information in a lower dimensional space. Figure 5 illustrates the process of the assessment task in urban planning. This task involves evaluating the performance impact of removing specific task components. The findings reveal that the removal of PlanGPT and PlanHS components results in score reductions of 0.7% and 3.6%, respectively. This decline underscores the importance of these components, particularly PlanGPT's superior expressive capability for urban planning texts. Additionally, PlanHS is noted for its effectiveness in handling texts with low signal-to-noise ratios, significantly improving information utilization and accuracy. In future work, the authors aim to refine the PlanGPT model by expanding large-scale pre-training efforts, specifically focusing on both urban and rural planning contexts to enrich the knowledge base. They also plan to investigate the application of multimodal techniques within urban planning, developing PlanVLM to achieve a more comprehensive understanding of spatial dynamics. Additionally, the authors intend to integrate AI solutions gradually by collaborating deeply with urban planning institutions to better understand practical needs, refine workflows involving large models, and effectively address procedural challenges in urban planning. In this paper, the authors introduce PlanGPT, which is the first large-scale language model framework specifically designed for urban and spatial planning. By adopting a customized approach, they successfully addressed key challenges in urban planning text management, review, and assessment, showcasing its efficiency and superiority in practice. This work represents a significant advancement in the integration of artificial intelligence with urban and rural planning, offering planners powerful support tools and enabling more intelligent and efficient decision-making in urban and rural development. Looking ahead, the authors plan to continue refining and expanding the capabilities of PlanGPT to further enhance its application within the urban planning domain. The author would like to express gratitude to the BCI Lab and the Natural Language Processing Research Group at Southern University of Science and Technology for their assistance in data collection and cleaning. This research was supported by funding from the National Natural Science Foundation of China, grant number 421712101, and the Shenzhen Municipal Natural Science Foundation, Key Project, Grant No. GXWD 2021231658007000810223326001. The development of PlanGPT has been further acknowledged in the references section. In this appendix, we delve into the process of fine-tuning instruction pairs for generating and evaluating text. The first section focuses on generating text that adheres to specific characteristics of urban and rural planning documents. This includes ensuring the text is coherent, uses formal language, and aligns with government document styles. The second section discusses style transfer, where the original text is rewritten to conform to these official document standards. The third section introduces a text evaluation system, where texts are scored based on their adherence to these standards, ranging from 0 for incomplete or off-topic texts to 3 for those that fully comply with the official style. Finally, we explore information extraction, where key terms are identified from given content to summarize the main points succinctly. Table 6 presents samples from the Urban-Rural STSB test, which includes a rating system for evaluating text completeness and style, keywords for information extraction, and questions from the Urban and Rural Planner Test V2. The table demonstrates the application of these elements in assessing and extracting relevant information from urban and rural planning texts. Table 7 presents a comparison of planning text generation models, specifically focusing on their outputs regarding the historical development and future planning of. The models included are PlanGPT, ChatGLM2 Shot, ChatGPT, and Baichuan 2-13B Chat. The text generated by these models highlight the city's historical significance, its transformation from a land trade hub to a maritime and land transportation nexus, and its current status as a major commercial city in northern China. The future planning aspect emphasizes the integration of various spatial plans to achieve, guided by the principles of the Communist Party of China and the strategic goals set for 2035. This table serves as a valuable resource for understanding how different models articulate the same planning objectives. Table 8 provides a detailed comparison of planning style transfers across different models, highlighting key historical milestones and transformations that have shaped the urban development of the region. It emphasizes the impact of strategic decisions, such as the integration into larger economic zones and the implementation of multi-plan unification, on the future spatial planning and development goals of the area. This comparison serves as a critical reference for understanding how different planning approaches influence the long-term development trajectory of cities like Jimo. Table 9 categorizes and describes various types of data related to land spatial planning. It includes data on provincial land spatial planning with 29 texts, municipal land spatial planning with 337 documents, and national land spatial master plans with 2,820 case studies. The table also provides details on data volume, sources, and remarks for each category, offering a comprehensive overview of the data available for land spatial planning. Thank you for watching.